This video we're going to look at how we differentiate the exponential function e to the x and the log function ln of x. Now ln of x, remember, is log to the base e, so it is a natural log. So two results here which we're going to use. If y is equal to e to the x, then dy by dx is still equal to e to the x. It's a strange one. Differentiate e to the x, you just get e to the x. Also, if you differentiate ln of x, then you get dy by dx equal to 1 over x. So these are the two most basic versions of this, and we're going to look at how we use these in a couple of examples. Okay, for the first one, you've got your dy by dx is just going to be equal to, so differentiate the 3x squared, you're just going to get 6x. Differentiate the e to the x, you'll just get e to the x. There was a minus 2 in front of it, so just put that in front of it again, dead easy. Now this second one, wee bit trickier. You've got to use your rules of logs here. So there's a rule of logs which says log of a over b is equal to log of a minus log of b. Now ln is still a log, so these rules apply. So you could rewrite your function y as ln of 1 minus ln of x cubed. Okay, there's another rule for logs, which is log of a to the power of n is the same as n times log of a. So we could change our we'll leave that as ln of 1 for a minute, and we'll change that to be 3 ln x. Okay, we're not done yet. Ln of 1 is 0. So if you just hit that on your calculator, you'll see that is true. And then if you differentiate the ln of x, you get 1 over x. Sorry, getting ahead of myself here. I haven't differentiated yet. I'll just change that back. That's still my ln of x. I'll tidy it up in a wee minute. And then if you differentiate, your dy by dx is just going to be minus 3 upon 1 over x. So that's me differentiating my ln, which is the same as minus 3 over x. Okay, so a couple more examples here. For example 3, we've got to find your dy by dx. So first of all, that's what we're looking for. I'm just going to change this at the start. I'm going to write that as ln of 4 minus, that's going to be ln of root x. Root x is the same, that's the same as ln of 4 minus, and that's going to be a half ln x. And that's because root x is the same as x to the power of a half. So we can use the rules of logs that we had said earlier on. Okay, ln of 4, first of all, ln of 4 is just a number. If you differentiate a number or a constant, you just get 0, so it's just going to be 0. And differentiate the ln x, you'll get 1 over x, and there was a half in front of it. So that's really what you have. And if you tidy that up, that's just going to be minus 1 on the top line and 2x on the bottom line, and that's it. Okay, example 4. Again, I'll rewrite this one a wee bit. This is 3e to the x minus 2 ln x. Then we're good to go. We're good to differentiate. That's just going to be differentiate e to the x, you get e to the x, and there's a 3 in front of it. Differentiate ln of x, you get 1 over x, and there was a minus 2 in front of it. So that's going to be 3e to the x minus 2 over x. Okay, a couple of results which are very good here, very helpful. First one, if you have y is equal to e to the ax, then dy by dx is equal to a e to the ax. So for example here, if I had y is equal to e to the 5x, and your dy by dx is going to be equal to e to the 5x and then times 5. Now the key thing to remember here is you have e to the 5x in the question, you have e to the 5x in the answer, so the power of the exponential part has to stay the same, and that's the same for all of these. Also, if you had e to a function of x, if you differentiate, it's still e to the function of x, but what is in front is the derivative of that function. And that's exactly what's happened here. So you have e to the 5x, you still have e to the 5x, and if you differentiate 5x, you get 5. So it's the same things happen. You have e to the function of x, and then when you differentiate, you've got that derivative of that function in front, and then e to the f of x. Okay, same idea. If you differentiate y equals ln of f of x, then dy by dx is equal to, so this function goes on the denominator, and its derivative goes on the numerator. So we'll see, we're going to prove this in this example using the chain rule, and then show a quick way of doing it as well. Okay, so quite a few examples to go through. The first one we're going to use use a chain rule to prove it. So here I'm going to say let y equal ln of u, and that means u is equal to 4x squared. So the two bits we need for the chain rule are dy by du, and we need du by dx. So dy by du will be, dy by du will be 1 over u. Du by dx will be 8x. So let's write down our chain rule again. Dy by dx is equal to dy by du times du by dx. And then if you multiply that, multiply those two things. First of all, I'm going to write my dy by du in terms of x. That's 1 over, instead of 1 over u, I'm going to write it 1 over 4x squared. And then my du by dx, I'm going to write it as 8x. Maybe makes it a wee bit easier for you to see if you write it as 8x over 1. And then top line becomes 8x. Bottom line is 4x squared. And that can just tidy up, running out of space here, but that can tidy up as 2 over x. Okay, that's fantastic, but the much quicker way of doing it, if you had y is equal to ln of 4x squared, then your dy by dx, just put the function on the denominator and the derivative of the function on the numerator, so it's going to be 8x. And then just cancel out as we did in the previous method, that's 2 over x. Okay, example 2, you have y is equal to e to the x squared. I'm just going to write that as, I'm not going to do anything here, so I'm just going to leave it as it is. I could have done this slightly different way. I'm going to differentiate, straight to it. And my exponential function was to the power of x squared, and then differentiate x squared, you get 2x, and that's it. So that's just from your y is equal to, y is equal to e to the f of x, then your dy by dx is equal to f dash of x upon e to the f of x. Now the key thing here, I've said this before, I'll say it again, your e is the power of f of x, and it's, when you differentiate, it's still the power of f of x. Okay, with far too many examples here, we'll just go through them very quickly. For this one, same idea, it's e to the f of x. The f of x is 5x squared. Differentiate the 5x squared, you'll have 10x. Over here for this one, very easy. You have got your e is the power of 2x minus 6. Differentiate 2x minus 6, you just get 2, and that's it. And a couple of trickier ones then. This one, for your y, first of all, I'm going to change my y how it is written. It's just very complicated looking. That's the same as 1 over e to the x to the power of a half on the bottom line, which is the same as 1 over e to the half x, which is the same as e to the minus a half x. So I've now got it in an index form. I'm good to differentiate. So differentiate, I'm going to have e to the minus a half x, and then differentiate the power, you're just going to get minus a half. So this is very complicated. Look, I'm just going to change it, write that as minus a half times, and that's now going to be 1 over e to the half x, and that's the same as minus a half times 1 over, and that's going to be e to the x to the power of a half, which you could write as minus 1 over 2 square root of e to the x. So just so that it's in the same form. To be honest, this, in my opinion, this is as nice a method, useful a way of writing it as any, but just so it's written back in the form that they used. Okay, your example 6. Example 6, you had got y is equal to x squared minus ln of, x squared minus 3. So differentiate, you're going to have x squared minus 3 in the bottom line. Differentiate your function, and you'll get just 2x. And have a look, is there anything you can cancel down? And no, there's not, so that's you done. Okay, over the page and on to example 7. It is ln of f of x, remember, so you put your f of x in the bottom line, so that's x squared. Differentiate your f of x, you get 2x. Have a look and see if you can cancel, and here you can cancel, so you must do that. So it's dy by dx is 2 over x. Your example 8. First thing I would do is I would rewrite this thing as y is equal to ln of x plus 2 minus ln of x plus 3, and then I'm good to go and differentiate. So I'm going to have x plus 2 here, and this is me differentiating my ln of x plus 2. X plus 2 is on the bottom line. Differentiate that bottom line, you're going to get 1. And over here, I've got x plus 3. Differentiate that x plus 3. I'm going to get 1 over here. And the only thing I would do in this particular one, just because it's quite nice, is I would take a common denominator of x plus 2 upon x plus 3. So this becomes x plus 3 minus x plus 2. Go back over your algebraic fractions if you need to. And then the bottom line stays the same. It's just still x plus 2 upon x plus 3. And the top line, if you multiply out that top line, you'll have x plus 3 minus x minus 2. So x minus x cancels out, and then 3 minus 2 is just 1. And that is it. And I wouldn't multiply it out. I would leave it as it is. Okay, our last example. Now, there's lots of different ways you could do this. One way I'm going to do it, I'm going to change this thing, rewrite my y. I'm going to write it as ln of x squared plus ln of, that should be now 1 plus x, and then minus ln of 1 minus x. And I'll rewrite that again. That's just going to be 2 ln of x plus ln of 1 plus x minus ln of 1 minus x. So when I did this first time, what I did, I split it up just to be ln of x squared plus 1 plus x squared upon 1 plus x, and then minus ln of the denominator. But slightly easier, maybe splitting it up into 3 simpler ln functions. They're just slightly easier to differentiate. It doesn't make a big difference really, but you can try it the other way and see how you get on. Okay, differentiate ln, you'll get 1 over x, and then that's being multiplied by 2, so it's 2 over x. And we'll have 1 plus x in the bottom line. Differentiate 1 plus x, you get 1. Over here, you're going to have minus, and then that's going to be 1 minus x in the bottom line. Differentiate 1 minus x, you'll get minus 1. So really, we have got minus times a minus here, so that's just going to be plus. We'll just change that. That's just going to be plus. Let me get rid of this one. There we are. So I'll just change that to be plus 1. Okay, you could take a common denominator. It's not a massive help in this one, to be honest. And your common denominator is going to be x upon 1 plus x upon 1 minus x. Now, hopefully you spot that 1 plus x upon 1 minus x is the difference of 2 squares. We'll see, because that'll come in useful when we do this. So this 2 up here needs to be multiplied by 1 plus x upon 1 minus x. So that's really 2 upon 1 minus x squared. And here, this 1 needs to be multiplied by x and 1 minus x. So that's 1 times x upon 1 minus x, which is going to be x minus x squared. And this 1 needs to be multiplied by x upon 1 plus x, which is going to be x plus x squared. So it's just x plus x squared. Okay, let's have a look. You have minus x squared and a plus x squared here. They'll cancel each other out. You have an x plus an x, so it'll be 2x. And then you have 2 times 1, which is 2, and 2 times minus x squared, which is minus 2x squared. So if you tidy that all up, you're going to have 2 plus 2x, 2 plus 2x minus x minus 2x squared, I should say, all divided by x upon 1 plus x upon 1 minus x. And there's nothing really you can do to make this much better, so I would just leave it as it is. Okay, you're now ready to do topic 6, exercise 2, questions 1 to 4 and 6, and exercise 3, questions 1 to 3.